So this is where I left off. I was getting a little bit of a chemistry review. We now understand that when you're looking at the periodic table, there are certain elements that will tend to give up electrons, and there are certain elements that tend to receive electrons. Remember, there are two conditions that atoms are looking for stability. They want to maintain charge balance. They'd like to have the number of protons in the nucleus equal to the number of electrons that are surrounding the nucleus of that atom. But by themselves, that's not often possible because the second condition is they want to have their valencies, right, satisfied in those orbitals or in those energy levels there. So they want to be filled to capacity. And so the reason elements will bond is that trade-off, trying to maintain charge balance while also filling valencies. And remember, we're trying to conserve energy, so atoms that just have a few electrons in their outer shell are going to tend to donate, right, or give or share those electrons with other atoms that tend to have just a few valencies that can receive those electrons. And so that's where we left off. This was the last slide I think I showed you, and it gives you not all the elements on the periodic table, but it shows you some of the common ones that we find in Earth rocks. And you can see the charge state there, right? You have a couple anions, A-N-I-O-N. Anions are the negatively charged atoms, right, that tend to receive electrons, so their net charge you're looking is going to be negative. And then there are a whole bunch of cations here. You can see from +1 up to +4. Note silicon, which is very important when we're going to talk about silicate minerals, has a charge of +4, and oxygen, which forms that silicate, which we'll talk about tetrahedron, or that molecule that is important for the building blocks of rocks, has a charge of -2. You'll also note here that the anions are typically, bless you, larger than the cations. And a few years ago, I had a student in the class that was a chemistry major, and they said that this diagram did not appear correct to them because it had chlorine being bigger than sodium atom. And indeed, we were both correct. They were correct in the sense if you're looking at a non-charged state where you actually are in a non-ionic state, where you actually have the atom not giving up or receiving the electron. So think about this, right? So if you're looking at just a sodium atom, right, that is not in an ionic state, that is not giving up the electron to the +1 charge there, you are going to have that electron in that outer orbital. So if you're looking at the ionic radius of sodium, right, which has not given away its electron, it's going to be larger, its radius, than chlorine, which is going to be the atom that receives that electron there. So this we're talking, bless you, the ionic state, and this we're talking about simply the representative element, right, without basically donating or receiving the electrons in its ionic state. So anyway, someone asked the question, so I want to make sure that that apparent inconsistency was resolved. Okay, it's not an inconsistency because we're talking about ionic state up here. Okay, and so here's our periodic table. As I said, we're going to focus on these two out here, +1, +2. These are the inert gases, right, that are clearly do not tend to bond because they have the valency satisfied in charge state. -1, -2 over here. We can look at +3, +4, and this can be either -3 or +5. Fortunately, most of these elements here are not important in rocks. Yes, nitrogen is a very important gas in the atmosphere, 80%, and it's important when you're looking at biological, right? Certainly, systems. But for rocks, yes, you do have nitrates and so forth there, but we're going to be focusing on these other guys here. And then in here are the transition metals. These are important. These are important because they tend to have loosely held electrons in their outermost orbital. These guys can have basically two valency levels, right? They can have an inner orbital that the valency is satisfied, and an outer orbital where the electrons are loosely held that can move from atom to atom, which is why metals are good conductors of electricity and heat, and they're also malleable. They can be pounded into sheets or ductile. They can be made into wire as well. It's because of those properties with those electrons in that outermost shell that are loosely held. Okay? So, like I said, that's all the chemistry I'm going to give you. Now, what I've done here is I just simplified the periodic table and put the important valency states here, +1, +2, right? And over here, the inert gases, -1, -2. I ignored in here. That can be -3 or +5, and then +3 and +4. And so, how does that work for bonding? Well, now what we do is we can look and see the elements in those particular columns, and they're going to bond with one another to achieve both charge balance and to satisfy valency here. So here, come back here, there's lithium, sodium in this column here, and there's -1 there. So if one of these guys bonds with someone here, right, this one needs one electron, this one gives up, then it's going to be 1 to 1. We put the cation first. So in this case here, if you're looking at hydrogen and it bonds with fluorine, it'd be hydrofluoric acid, right? HCl, hydrochloric acid, right? HCl. Okay, lithium fluoride, right? Sodium fluoride, right? Sodium chloride, right? NaCl, 1 to 1. If we come over here, +1 to -2, well, oxygen needs 2 electrons to satisfy, so it's going to require, in this case here, Na, two of them, so we always put the number as a subscript. So it'd be Na2, oxygen, O. It's that simple. when you're writing down the chemical formulas for these. And so what I'm showing you here is an ionic bond between lithium and fluorine, right? Fluorine has one valency, lithium has this extra electron here. To conserve energy, it's easier to give up that electron, and it creates an ionic bond. So at that point there, lithium has 3 protons in its nucleus. You'll say, well, Terry, there's 2 electrons there, but don't forget, the bond is created, and so that electron, of course, has been basically transferred over to this valency here, but by having that bond between those 2 elements, lithium maintains its charge balance, right? So even though you got 9 here, but 1, 2, and 8 out here, that's 10, right? You'd think, okay, well, that's a net negative charge, but no, it's because it has that bond with lithium. When you transfer an electron, we call that an ionic bond. You're physically transferring the electron from the donor or the cation to the anion, okay? Sodium chloride maintains an ionic bond as well. And so, again, just for the chemical formula, just keep track of the number of valencies and the number of cations that are necessary to fill those valencies. And then the number of the atom will be a subscript. And there is no subscript if it's 1. It's just LiF, lithium fluoride. Sodium chloride, right? There's sodium. You can see the same thing, 1 electron here. It's easier to give up 1 than to take 7. Chlorine has 1 valency, and so you transfer the electron. That's your ionic bond that makes up salt, or table salt, right? Or halite is the name of the mineral you'll be learning this week. And then I had you note earlier that when we're looking at the primary elements that make up Earth rocks, crustal rocks, and the mantle rocks, the silicate minerals, that you have an Si plus 4 and an O minus 2 charge. The bonds between these guys are not ionic bonds. They are covalent bonds. And these are the bonds that we see with water molecules between hydrogen and oxygen. And so a covalent bond, if you're thinking of the ratio, it's similar to the ionic bond, right? So in this case here, hydrogen has 1 electron that's available, right? That can be, in an ionic bond, can be transferred, but in a covalent bond, it's actually shared. You'll notice the bonding is a little bit tighter, right? The atoms are actually touching the outer orbitals or valencies here when you're looking at the energy levels here. So what happens here, remember, oxygen is minus 2. It has 2 valencies. Hydrogen has 1 electron available. So what happens here is oxygen and hydrogen will share each of their 1 electron that's available to share here. So that'll satisfy that valency. So now you have 2 electrons in that inner orbital, right? So the valencies are filled to capacity. Because you're sharing it, it only has 1/2 a value. So 1/2 of 2 is 1, and so 1 proton to 1 electrical or negative charge, right, is balanced. And then the second valency is satisfied over here. You'll notice the molecule has a shape to it. It looks like Mickey Mouse, right? You can see the oxygen atom here and the 2 hydrogen atoms. And that's important because what happens here when you actually look at the water molecule, right? To break up a water molecule takes a lot of energy to actually break up the molecule itself, to separate the hydrogen from oxygen. But to actually, when you're looking at water freezing and crystallizing, it's actually crystallizing and forming what we call van der Waals bonds or intermolecular bonds. What happens here, when you look at the molecule, you'll notice that there's a whole bunch of the electrons over here. So on this side of the water molecule, it's a little bit negative. It has a slightly negative dipolar charge on this side. On this side of the water molecule, it has a net positive charge, right? Because the electrons are this side. What happens here when when you start to lower the temperature and it starts to freeze, is this negative side will form an intermolecular bond with this positive side, forming a water crystal. Which is why water has such a low melting temperature, because what you're doing when you're melting water, you're not breaking up the hydrogen to oxygen atoms inside of the molecule. You're actually breaking the intermolecular van der Waals bond, which is a very weak bond. It's the same kind of bond that we see with graphite between the sheets of carbon, that rubs off with the pencil there. And so water will make intermolecular bonds between the molecules, and when it's melting, that's what you're breaking. Okay, the intermolecular bond, not the actual covalent bond between the hydrogen and oxygen atoms in the molecule itself. Yes?
So is van der Waals bond just the general term for partial negative?
Yes, there's different kinds. Like there's clearly the situation with water. In a sense, you have intermolecular bonds when you're looking at even when you have very, very low near absolute freezing temperatures. When you think about how do you solidify helium and neon, when those are just kind of very brief moments where you'll have some, the electrons will be on one side giving a net negative charge and a little bit positive charge, and those are van der Waals bonds as well. So any kind of intermolecular bond like that, yes. I'm going to actually talk about van der Waals bonds. Okay? So those are covalent bonds at that point there. There are some other types of bonds that come into play here. There's metallic bonds that are important for the transition metals, and then there are intermolecular bonds, which I just brought up in that discussion about water. Okay? So I'll briefly just go over these just so you're familiar with the terminology. The metallic bonding, right, occurs, as I said, primarily in the looking at the metals, right, where you have these free electrons. And if you look at, for instance, iron, we're going to talk about iron oxide. If you're looking at iron that's present in a silicate mineral, like in pyroxene or olivine or the ferromagnesium minerals, right? You're going to have iron is going to bond with a silicate structure. You're going to have iron oxides, right? That iron that you find in minerals has a charge of +2. So it can have multiple valency states. It has a charge of +2. So its chemical formula is FeO, that iron oxide. When you bring ferromagnesium minerals to the surface, or steel or anything with iron in it, and it rusts, right, in the presence of oxygen and water, it produces iron oxide, hematite or rust, right? That is iron with a charge of +3. So you can have multiple valency states, and copper and a lot of these metals have the same thing here related to the valency state of these particular metals here. And the other important thing to note about the metals, right, is they will tend to have two orbitals which can have valencies on them. You can have an inner orbital and an outer orbital. The outermost orbital, right, you don't have to satisfy the valencies. Those electrons are free to move from atom to atom, right? And so we talk about these electrons as being delocalized, sort of an electron sea or an electron cloud with these metals. And so the strong bond is actually in the interior, right? When you're looking at satisfying the interior valencies of the inner shells of the strong bond. And then you have these free electrons that can move from atom to atom. And that's going to be important because it's going to be important for defining the attributes that make up metals, including their ductility, their malleability, aluminum foil, right? These very thin sheets because of the fact that these electrons will move as you're pounding and compressing, right, and making the sheet of aluminum or other metals that can make sheets as well, gold sheeting, for instance, as well. And so this just kind of shows you some of the physical properties of these metals here. Conductors of heat and electricity, high melting points, malleable, ductile, right? They're opaque, and they have that metallic sort of reflective luster there that you can see. And over here shows malleability and ductility and how these, when you're looking at the nuclei of these atoms, it is these electrons, right, are able to move or roll past because they're not fixed in a set crystal lattice as you see with the interior electrons. Van der Waals bonds, right? And so, I'm sorry, who just asked about van der Waals bonds? What's your first name again? Adolf? Adolf, yeah, so Adolf is correct. That van der Waals bonds, right, are general terms we use for intermolecular connections. And so, in what we're looking at here is even in a situation where you don't have a molecule like water, where the molecule itself kind of arranges one side of it to have a more negative side and the other side to have a positive side, if you're just looking at any kind of, atom, right, that is in space, in this situation, your electrons in those orbitals are going to be organized, and it's kind of a statistical organization that any given time in space, an electron will be in a certain position around that atom. So because of that, there's going to be time periods where you might have more electrons on one side of the atom for that brief moment. So for that brief moment, you're going to have a negative dipole on that one side where you have those electrons arranged. So if there's another atom that is in close proximity, right, then what's going to happen there is it's going to attract the more positive side. So you can even have at really, really low temperatures, like going down to absolute zero, that is how you can solidify the inert gases. Right, the bonds that are forming there are these van der Waals bonds, right, where you have this brief dipole moment where you have these negative and positive charges line up there. Okay, so it can simply be just ephemeral, right, with just clearly statistical probability of where those electrons will be. And then once, of course, you form that bond, it remains there if the temperature is low enough and you're not raising the temperature where you excite the atoms where you can break that even very weak bond. But as I mentioned, with water, you actually have a molecule that is going to put a situation where you're going to tend to have a positive dipole side and a negative dipole side here. So this is referring to, again, a van der Waals bond, and often referred to as hydrogen bonds in water, right? So same idea, though. It's an intermolecular bond that you've satisfied the valencies within, right, the atom and its charge state, but the bond is being made between the negative and positive dipoles. In this case here, related to the shape or configuration of the water molecule and how those hydrogen atoms are arranged with the oxygen atom. And I just remind you, when ice melts, the intermolecular bonds break, not the covalent bonds. So you're breaking this bond, not those guys. That takes a lot of energy to break the hydrogen and oxygen that holds the water molecule together. And as I mentioned earlier in lecture, that is the weak bond between the carbon sheets, right? You have covalent bonds within the carbon sheet and then van der Waals bonds between the carbon sheets. And that's what's breaking and leaving the trace of carbon on the paper. All right. So now, when we're looking at the properties of minerals, and that's what you're doing in lab right now, a group of you had lab this morning. And so you were looking at attributes of these minerals, and you were using these attributes to help you classify minerals. And as I said, you're learning 14 minerals. And those attributes can be tied very strongly to the chemistry, right, of the mineral. And so you're thinking about hardness, which is one of the attributes you looked at. Diamond has a hardness of 10 on the Mohs scale. Talc, graphite have hardnesses of 1. That hardness scale is ranked from 1 to 10. There are certain index minerals that we use to define each number. Quartz has a hardness of 7, for example. Calcite has a hardness of 3 on that Mohs scale. The Mohs scale, the hardness scale, is not a linear scale, right? It is a relative scale. So when you're looking at diamond having a hardness of 10, diamond is not 10 times harder than talc. It's actually more than 2,000 times harder. So it's just a relative scale for ranking hardness of minerals. But the hardness of the mineral is tied to a lot to the chemistry, the bond strength, right? Graphite and talc, right, are weak because of the weak van der Waals bonds between them. And minerals, you're learning about cleavage today, and you'll learn about this week for those who haven't had lab, where you have weakness planes where minerals tend to break off. Those cleavage or weakness planes are defined largely between differential bond strength within the mineral itself. And so where you have bonds that are going to have a greater propensity for breakage, as long as there's a plane that is continuous throughout the mineral, then it's going to continually break along that same plane and repeat itself throughout the mineral structure. The crystal face, the crystal form, is related to how those atoms arrange themselves as the mineral is constructed or beginning to build as you get to its freezing point there. This is a dentist drill, just reminding you that you're glad your dentist has diamond tips on the drill, because you'd hate if they were using apatite, which is the mineral your teeth are made out of, because they'd be drilling a long time, right? The hardness of diamond is such that it very easily can drill through the apatite or enamel on your tooth to repair or fix a cavity. And I showed you this earlier. We talked about minerals, looking at graphite versus diamond, weak van der Waals bonds, right, between the sheets, and diamond has covalent bonds. This artwork, by the way, this was shared with me with a colleague of mine way back in I think probably the late 90s and 2000s. So I've just kept it. These were the actual proofs that went into the textbook. So I kind of liked the artwork. And so I just kept some. And you'll see some older slides. My advisor, prior to his passing, shared a lot of his lecture slides that I had. So I've kept some of these old famous Shelton geomorphic slides. So you'll see some historical slides in here as well. Yes?
So if our teeth are a mineral, but then they're like organic?
Then it would be true to say that, yes, it's apatite, but in a purer sense, it wouldn't be classified as a mineral because it was organically derived. That would be correct. Yeah, so I was only giving this an example for hardness, that it's made just like calcite in a shell. Yes, if we're going to be purists about it, we would say, no, that's organically derived. But I'm glad you pointed that out. Yes, you are correct. And then other things you'll be looking at here, especially with the metallic minerals, is they will all leave distinct streaks on porcelain plates. So when you're in lab this week, we ask you not to streak the non-metallic minerals, because that's not diagnostic of the mineral. There are 3 metallic minerals in the lab that you will learn this week. One of them is hematite, iron oxide. And hematite, even though it looks, clearly it's metallic luster to it, when you streak it, it leaves that typical reddish brown rust-colored streak. And it's always diagnostic of the mineral hematite. And I won't mention the other 2 metallic minerals because some of you haven't had the lab yet, so you'll learn that. But hematite is one that I will mention. Okay, it does have a distinct streak that it leaves on a porcelain plate. Right? So you're going through today in lab and you're using a dichotomous key. As I said, the first subdivision, metallic, non-metallic, then you get, right, that separates them. Then you go through a key for metallic minerals, and you key them out when you have one. And then there's a non-metallic. And then it's light, dark, and then harder than glass, softer than glass, and so on. And you work your way through until you end up with the criteria necessary to be able to classify the mineral. And as I said, we don't give you mineral keys for all 3,000 minerals. We try to give you, mineral keys that we don't give you all, right? We give you more than the minerals you're actually classifying, just so it makes it a little bit challenging for you, but not to the point where, oh my God, I'm so overwhelming, okay? So that's kind of what you're going to be doing this week in the lab, is applying what we're learning in the lecture hall, particularly the chemistry side of things. Now, let's look at the silicate minerals, right? Since they're the dominant minerals. The Earth's continental crust and ocean crust is largely made up of silicate minerals, as well as the mantle. There are other mineral groups. Probably the next most common mineral group would be the carbonates. That would be limestone, calcium carbonate, calcite. Right? Limestone, right, is a rock that makes up a substantial proportionality of sedimentary rocks, particularly in marine settings there. Okay? But most of the rock, if you're looking at volume for the Earth, is going to be silicate minerals. And so when you look at your typical Earth rock and you look at the breakdown, right, of the elements, you can clearly see the silicate, right? Silicate and oxygen dominate, right? Almost 2/3 here. I can tell by looking at this common rock. This is another artwork from that textbook way back. You can see why I know this is continental crust is because I don't see magnesium there in any dominant amount, right? Mg plus 2, but you'll notice I list magnesium over here. And I can see sodium and potassium, which tells me those are lighter elements, so they're common in granite. The pink feldspar, that pink mineral you guys learned today, this morning, that's potassium feldspar. And then also sodium-rich plagioclase. So the potassium and sodium tend to be coincidental with the felsic or the continental crustal silicate mineral rocks, okay? But anyway, if this was an ocean crust, you'd probably see not much of that, but you'd see magnesium over here, okay, being on there. But I listed up there. The important thing to note is if you look at all the other elements, right, silicon is +4, oxygen is -2. All the other elements that make up rocks are cations. They're all positively charged atoms, right, or will tend to give up electrons, right, in their bond. And so that tells you something. They're bonding with silicon and oxygen or silicate structure. What does that tell you about the charge state of the silicate structure if everything that's bonding with it is cations? It's negative, and indeed it is. The silicate structure that you find making up those minerals that make up the crust and the mantle, olivine, pyroxene, amphibole, right, biotite, muscovite, sodium-rich plagioclase, calcium-rich plagioclase, orthoclase or potassium feldspar, and quartz, right, all are comprised of silicate tetrahedron. Tetrahedra, right, hedron is one, hedra, H-E-D-R-A, is the plural for that state. So when you're looking at silicate tetrahedra and you actually look at the molecule, indeed, you can see you have one silicon atom that is in the center of this pyramidal shape, this tetrahedron, which is a four-sided pyramid. And so oxygen has a charge of -2, -2, -2. What's the net charge of this molecule? Si, the positive, O4. What's its net charge? -4, because -2 times 4 is -8, plus 4, right, -4. So it's SiO4 -4, which is what I have here. And so in order to satisfy, we call this an anion, but it's a complex anion, right? You can look at nitric acid, right? Hydrogen, when you look at acid, hydrogen is the cation, right? HCl, right? H plus 1, Cl minus 1. Nitric acid, NO3. NO3 is the complex anion. It's a molecule. It's not just a single atom. So when you're looking at the silicate tetrahedron, SiO4 is a complex anion. And it bonds with cations. The way to achieve charge balance, right, is by, one, it can form ionic bonds with available cations, right? So we can go back. All these are cations. So these can bond, right, with these valencies. So each of these oxygen atoms has one valency, right? There's a covalent bond between oxygen and silicon. Each of these oxygen has a covalent bond between the silicon atom in its mantle and the oxygen atom. And that leaves one valency for each oxygen atom. That valency can be satisfied by two primary bonding mechanisms. One, bond directly with cations, ionic bonds, or two, share electrons between adjacent tetrahedra. So you form covalent bonds between tetrahedra, which means you can create tetrahedral chains, tetrahedral sheets by forming these covalent bonds. That's the two ways. So when I show you each of the minerals where I'm going to next, I'm going to start with the highest freezing melting temperature silicate mineral in the mantle, olivine, and I'm going to work myself through going to progressively lower and lower freezing melting temperatures till I end with quartz, which is the dominant mineral in the continental crust. And so when I'm showing you these molecules, if you see the oxygen atoms touching between the tetrahedra, that's designating a covalent bond sharing electrons between those oxygen atoms. If the tetrahedra are apart and I show other little atoms bonding with them, those are ionic bonds with the available cation. So we're going to start with olivine. Olivine, always green. It doesn't fit the generalization. It's a ferromagnesium-rich mineral, meaning it's iron magnesium rich. If you look at its chemical formula, there's the SiO4, and it's bonded almost exclusively with magnesium and iron. Those two elements, those atoms. Another chemistry rule, again, if you haven't had chemistry in a while, when you have a parenthesis with elements present with a comma, it means that magnesium and iron can ionically substitute for one another to satisfy these bonds, these ionic bonds. So you can have an olivine. Olivine is actually a mineral group. Olivine can be an iron-rich mineral, or it can be a magnesium-rich mineral, or it can be 50-50. So those elements, iron and magnesium, can exchange in that structure. They both have a charge of +2. Mg +2, Fe +2. And I said iron has a +2 charge in a mineral state. When it's oxidized on the surface of the earth, in an oxidized state, it's Fe +3. It's ferric iron. That's why the formula is Fe2O3. The formula here is if you're looking at just the iron oxide, it's FeO in the mineral. You'll notice the artist shows, and again, this is from that same textbook artist, it shows the tetrahedra isolated, independent. And so these oxygen atoms, each one of them has one valency, right, is being satisfied by bonding with magnesium or iron. So remember, Fe +2 times 2 is +4. That's -4. Or Mg +2 times 2 is +4, -4. It's bonded. It has charge balance, and you've satisfied the valencies by forming ionic bonds with the valencies of those oxygen atoms. You're thinking, oh my God, all this chemistry and all these. You don't have to memorize this stuff. Remember, it's an open note test. I will give you these images on the exam, and then you can use the images to actually calculate the ratios of silica to oxygen and so forth. Okay, you don't have to memorize all this stuff. It's the major mineral comprising the mantle, olivine. And as I said, it doesn't fit the pattern because most ferromagnesium minerals are dark, black, right, when you're looking at basalt and pyroxene and amphibole and biotite. But olivine, if you hold it in your hand, it's dense, right, because of its high ferromagnesium content. It's made of dense elements. And so I ask you, if you're looking at there, what's the ratio of silicon to oxygen in the olivine structure? So you have to take a tetrahedra. How many silicon atoms are in this tetrahedra? 1. How many oxygen atoms are surrounding it? Are those oxygen atoms shared with any other tetrahedra based on this diagram? No, they're not. So 1 silicon to 4. So the ratio of silicon to oxygen is 1 to 4. What I want to show you here when we look at these ratios, as we start forming more and more covalent bond, you're going to see the ratio of silicon to oxygen to going up. And what that tells you is as we get to silicate minerals with lower freezing melting temperatures, the silica content goes up, their magnesium content goes down. They're inversely related. Okay, so that's your independent tetrahedron. Next, we're going to look at the common mineral, one of the common minerals in basalt. That is the mineral pyroxene. You won't meet pyroxene until next week in the Igneous Rock Lab, so you don't see pyroxene this week. Pyroxene is a single-chain silicate structure. You can see for the first time we have oxygen atoms touching meaning they're satisfying their valencies by forming covalent bonds by sharing electrons with one another. You can see that the unshared oxygen atoms are satisfied with ionic bonds with available cations. What are the ionic bonds? Well, it can be any of these. So pyroxene is a mineral group. It's the mineral group that's, when you're looking at that semi-precious stone, jade is a pyroxene group mineral, a more greener color of it. But as I said, the chemistry can vary depending on which of these elements ionically substitute for one another in its composition. We call it a single chain silicate structure. You think of a gold necklace, single chain, you just have the rings with two contact points, right, of that chain. So if you're looking at this, pyroxene, right, a couple things that stand out. One, if you look at olivine, right, it does not have any kind of distinct plane at which it breaks. Olivine fractures. It has no weakness plane. Pyroxene, because of the chain structure, you'll notice that there's a plane here with ionic bonds, and then what you can't see because of the two dimensions here, this oxygen atom is also unshared. There's also a plane out here of ionic bonds that can be broken. So there's a plane here and a plane here. So pyroxene has two weakness planes at 90 degrees because of its chemistry. It's one of the dominant minerals in basalt. There's two primary dominant. You can have olivine in basalt, but it's typically going to form phenocryst, right? It's an early form crystal, and it'll form green phenocryst in basalt. But basalt is dominant by pyroxene and calcium-rich plagioclase, which I'll get to later. The ratio of silicon and oxygen is 1 to 3. How do you figure that out? Well, take your typical tetrahedra. Every one of these tetrahedra have 2 shared and 2 unshared, right? Oxygen atoms. 1 silicon atom in the middle. So if you're sharing, what's your name again? Oscar. So you and I have 2 apples, right? We're sharing them. How many do we get each? 1. If I have 2 apples and I'm not sharing them, how many do I get? 2. I get 2. So if you're looking at over here, right, you can see in the case of every time you have shared oxygen atoms, you need to think about that they're being shared between the tetrahedra. You have to subdivide. So if you have 2 shared, right, for that tetrahedra, that's going to only represent 1 total, right, charge when you're looking at that, right, because it's sharing it here. So if you're counting this up, the ratio of silicon and oxygen, you've got 1 silicon atom, 2 unshared, right, so that means 2, plus 2 shared, 2 divided by 2 is 1. So the ratio of silicon and oxygen is 1 to 3 for each of these tetrahedra. Is that agreeable to everyone in this class? Is 1 to 3 a bigger ratio than 1 to 4? Is 1/3 bigger than 1/4? Yes. So would you say this is more silica rich than olivine? If the SiO content, right, if it's 1 to 3? Yes. And so even though there's iron magnesium present here, right, with olivine, iron magnesium, right, those are the only elements here. So here, remember, some of these valencies are being satisfied with covalent bonds, so the iron magnesium content has to be less than for olivine. Amphibole. This is a dominant ferromagnesium mineral in intermediate composition rocks. Andesite, dacite to a little bit less dacite, but certainly andesite, or the coarse-grained equivalent of andesite, diorite. These are the igneous rocks that form at subduction zones, partial melt of basaltic ocean crust. Amphibole. Hornblende is a type of amphibole, right? So in lab, you're looking at hornblende samples. Hornblende is just a type of amphibole. Amphibole is a double-chain silicate mineral group. So any of these elements can ionically substitute in this structure. These elements here are forming the ionic bonds for the unshared oxygen atoms that need to satisfy valencies by forming ionic bonds with available cations. So remember, this formula, these elements here can vary. They may not even be present in amphibole, but they can be. They can substitute for one another. You'll notice a double chain, right, silicate structure. Those are strong bonds, right? You now have a second bond there. It's not just a single chain. But makes it complex. One thing I want you to note here is OH2. You're seeing water for the first time in the chemical composition of a silicate mineral. Where does that water come from? It comes from the subduction process. You're subducting clay minerals on the ocean floor that are hydrous minerals. You've got water getting taken down the subduction process. When that mineral crystallizes, amphibole is one of the minerals that can hold water in it in fluid inclusions. Okay, so it's a hydrous mineral. It has water present from the subduction process. And so when you're looking at the ratio of silicon and oxygen, it's a little bit more complex. You look at this tetrahedron here, how many are shared in this tetrahedron, oxygen atoms? Is that shared? Is that shared? Is that shared? Is that shared? No. So that's the same as like the pyroxene, right? 2 shared, 2 unshared. So it's 1 to 3, right, is the silicon-oxygen ratio. Would you agree with that? How many are shared here? 3, 1 unshared, right? So 3 shared, 3 divided by 2 is 1.5. 1 unshared, 1 divided by 1 is 1. 1 plus 1.5, 1 silicon atom to 2.5 oxygen atoms. 50% 1 to 3, 50% 1 to 2.5. What's the average of 1 to 2.5 and 3? Yeah, 1 to 2.75. Is that a bigger ratio than 1 to 3? Yes, it's more silica rich. If it's more silica rich and you're taking up more, satisfying more valencies, then you're going to have less opportunity to bond with iron and magnesium. And you can see, yes, iron magnesium is present there and has a dark color to it, but you'll notice, again, that the iron magnesium content is going down as the silica content goes up, because you're having more and more covalent bonds that are removing those valencies that are available to share with cations, or excuse me, to bond with ionic bonds with cations. Okay? You don't have to worry about memorizing this. These diagrams will be given to you on my exams. You'll be able to see them, because I think if you're not a chemistry major, some of you might be able to go and look at the chemical formula and work through all this, but if you're not, it's easier if you can just see the actual picture of it and then look at those ratios by counting up the number of shared and unshared, which is what I've done for you here. We're going on down. Biotite and muscovite, the micas, the sheet silicates. Like the amphibole structure, going back here, because of the fixed, again, lattice structure, right? When you're looking at the crystal structure, there are 2 cleavage planes, right, with amphibole, and they're 2 not at 90, right? They are basically 124 and 56 degrees. I was like students think of 120 and 60. You can think of triangles that way, but it's about 124 and 56 is the actual cleavage plane. So 2 not at 90 degrees is the weakness plane. You can actually see them present on this crystal here. The sheet silicates, right? And they're self-describing. You can see now you have 3 shared and 1 unshared. You've already calculated that ratio. What's the ratio when you have 3 shared and 1 unshared? 3 shared, 3 divided by 2, 1.5. 1 unshared, 1 divided by 1 is 1. 1 plus 1.5 is 2.5. 1 silicon to 2.5. Is that bigger than 1 to 2.75? Yeah. You'll notice biotite mica, which is the dark mica, has iron magnesium present. Muscovite, which is clear, does not. They're both sheet silicates. There's 1 cleavage plane, right? And it's the unshared, right, oxygen atom that's being satisfied as valency with ionic bonds between the sheets. There are strong covalent bonds within the sheets, and so it tends to break off at planes of 180 degrees. They're stacked on top of one another. They both have water dissolved in them. They're hydrous minerals. They're subduction zone minerals and also found in granite, continental crust. And so you say, well, Terry, where's the water coming in the continental crust? Remember, continental crust forms, when you're looking at granite, it forms when continental crust collides. Well, if continental crust is created by basically subduction, then the water that is present in the hydrous minerals in the continental crust, when it collides and partially melts and forms granite, you still have to have a placeholder for it. So the muscovite and biotite are going to be minerals that can hold water. The ratio is 1 to 2.5. I should move that down, sorry, on that slide there. The last thing I want to mention, I'll cover the plagioclase and the feldspar minerals on Wednesday, and then I'm going to start getting into igneous rocks. Let's just mention quartz before you go. We've now reached the point where you have all of the oxygen atoms shared with one another with strong covalent bonds. This, you can see why quartz does not cleave. It has no weakness planes. It has equally strong covalent bonds throughout its structure. And so if all the oxygen atoms are shared with covalent bonds, you have 4 shared. 4 divided by 2 is 2, right? And you have silicon, so 1 silicon, 4 shared, that's 1 to 2, SiO2, right? And quartz is pure silica. No cleavage planes, no weakness planes. It fractures. The bonds are strong throughout. Okay? And what I will discuss on Wednesday is we'll talk about the plagioclase and feldspar structures, the minerals I've not mentioned. Okay, they're a little bit more complex. Okay, but those are the main silicate minerals, and those are the silicon to oxygen ratio, and you can see why the ratio of silicon to oxygen goes up as you increase the number of covalent bonds between tetrahedra. All right, have a nice day. And I will extend those things I said I would when I get to my computer.